Now we are going to start to cover bonds that are not covalent. We've already talked about covalent bonds, how they are the sharing of electrons, and how they're the most important bond for building the big biological molecules that we care about: proteins, lipids, nucleic acids, and carbohydrates. But covalent bonds are not the whole story. We have other bonds that are important as well: ionic bonds, hydrogen bonds, and van der Waals forces. So let's cover ionic bonds first. Okay, so ionic bonds have to do with ions. Ions are simply atoms or molecules or parts of molecules that are charged. Okay, so by charged, I mean they have a positive or a negative charge. And again, this has to do with electrons and protons. If we have more electrons than protons, we have a negative charge. If we have more protons than electrons, we're going to have a positive charge because protons are positively charged and electrons are negatively charged. And ions are critical for our body. They're critical for maintaining homeostasis. So I'm sure you've heard of things like sodium ions, potassium ions, chloride ions, magnesium ions, calcium ions. Okay, notice how all of these are atomic symbols with a plus or minus or 2 plus or 2 minus next to them. So these are all atoms that are ions. We also have things like bicarbonate, okay, HCO3. So this is a small molecule that is in fact charged, critical for homeostasis in terms of blood pH. All right, so that's what an ion is. And an ionic bond is the attraction between positive and negative. Okay, so these are attracted to one another, and that would be an ionic bond. All right, so how do things get positively or negatively charged? Well, one thing that can happen is we can have electron transfer. So let's remember once again that atoms want that full outer valence shell, and if they don't have it, they're going to react with other atoms in order to have a full shell. So let's draw an example of what electron transfer might look like. And let's go ahead and do that with potassium and chloride. Okay, so potassium. Okay, so potassium has an atomic number of 19, which means 19 protons and 19 electrons. So we're going to draw 2 in that first shell like we always do, unless we're hydrogen. And then in the second shell, we're going to draw 8. Okay, so here's 8, and then we're actually going to need a third shell. Okay, and we're going to draw 8 in this shell as well. So 8 plus 8 is 16, plus 2 is 18, which means we need one more shell. Okay, so we need this fourth shell. Now, for the important atoms that we care about the most, so carbon, nitrogen, oxygen, and hydrogen, we're not going to have to go out to this fourth shell, but of course atoms can't do that. All right, and then next to it, let's draw a molecule of chlorine. All right, so our atomic number is going to be, in this case, 17. So 17 electrons. All right, so here's our atomic nucleus, so chlorine. Here's our first electron shell with 2 electrons, second shell with 1, 2, 3, 4, 5, 6, 7, 8, and then a third shell, and that is going to have 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so look at these 2 atoms. Are they happy and stable in this configuration? Well, no. Potassium is really not happy with a single electron in that outer shell. It would like to give this electron up because the next shell, that inner shell, is in fact full. And chlorine is unhappy as well. It has 7 in that outer shell and it wants 8. Okay, so one thing that can happen is this electron can actually be sucked away by chlorine. Okay, so it can leave potassium and it can go to chloride. And then we can get rid of that outer shell. Okay, so it can just sort of disappear. All right. And now Potassium is happy because its outer shell has 8 electrons, and chlorine is happy as well because it has 8 electrons in its valence shell. Okay, but now both of these have a charge. So our potassium is now positively charged. Our chloride ion is negatively charged. And now these two atoms will actually be attracted to one another because of that difference in charge. So that's what an ionic bond is. It is the attraction, once again, between positive and negative. All right, and by the way, once again, this is based on electronegativity. Remember electronegativity? That's the affinity of an atom for electrons, okay? And there's a big difference in electronegativity between these two. Potassium has 0.82 electronegativity. Chlorine has 3.19. So it is so much better at taking electrons that it's actually pretty much going to take it all the way. And that will become sort of a permanent feature of the chloride ion. All right, and you know what? Ionic bonds matter a lot in molecules. Let's take, for example, proteins. Definitely one of our very most important class of molecules. Well, proteins are long chains of amino acids that are folded up, and they have all these side chains that are interacting with one another. And sometimes they have an interaction that is an ionic bond. So for example, sometimes you'll see something like this. So an amino group here, and then you'll have a carboxyl group next to it. And we don't need to know what these things are so much right now. But one thing that can happen, particularly right here, is that this OH group, oxygen can actually just lose this hydrogen, but keep the electron such that it becomes negatively charged. Nitrogen, on the other hand, can sort of pick this up, and this group can become positively charged. So once again, we have a positive and a negative charge next to each other, and that is actually going to cause an ionic bond right within the three-dimensional structure of this protein. Okay, ionic bonds are strong and they're important. So it's something that we're going to want to be aware of as we start to look at molecules.